we can derive the Poisson's distribution or Poisson distribution from the point of view of the binomial distribution. That means whenever n goes to infinity, whenever n number of trials goes to infinities, that means very large, and the probability of success is very small, tends to 0. In that limit, the binomial distribution becomes a Poisson distribution. Now we are deriving or understanding the Poisson distribution, or rather Poisson process, in a different manner. That means a queuing manner, in a queuing process idea, the idea of queuing process. That means, supposed to be I have some radioactive substance where nucleus undergoes some disintegration, and it emits different kinds of particles, alpha, beta, or gamma radiations. Supposed to be the particles are emitting, for simplicity, for the sake of simple thought, the particles are emitting from the radioactive substance. And if we observe by a detector, then we see that some particles are emanating from that substance. And from the point of view of the atom, which atom will disintegrate, that we don't know. But some atom will disintegrate at any time, that is random event. But the average rate at which the particles are emitting from the substance to a detector, that is almost fixed for a given substance. That means we know how to the half-life of a radioactive substance. That means it decays half of the particles of the initials. And if that is value, and if my observation is limited, is very less than to the half-life of the substance, then you can think radioactive decay process as a rate is constant. Rate is almost constant, the rate at which the particles are disintegrating, but which atom will disintegrate, that is unknown to us, and that is random here. Average counting rate does not decrease during the experiment. That is very vital thing. And basically the Poisson process is the process where the sequence of discrete events occurs, but the average time between two events is almost constant, and but the timing of the particular event or particular radioactive substance decaying, that is unknown to us, right? And average counting rate does not decrease during the experiment. That is very vital. Now for the sake of simplicity, we think the probability of one particle will be emitted during the time interval delta t is proportional to the interval delta t. That is suitably chosen for a given experiments. What will be the exact value of delta t? It depends on the process. I am taking the delta t in such a way exactly one particle or one event will be detected at the time. This is the way I am modeling this situation. That means I can say the probability of probability p subscript 1, that means the probability of happening one events, that means probability of emitting one radioactive particles is delta t, is proportional to delta t. That means the probability of one particle emitted, that means some constant lambda times delta t. This is my equation number 1. And this is my equation number 1. And this is I am assuming that it is small enough to consider the two particles are emitted in this interval. That is my assumption. It is such a way chosen or small that no two particle will be emitted in this interval, only the window for one particle. That is our assumption, or that is our premise. Now let us consider our question is the probability of observing n counts in the time interval t plus delta t. That is our main question. In t plus delta t time, in t plus delta t interval, the probability of happening exactly n events. That is our main question, and that can be think of it as the probability of observing or detecting n events, exactly n events in time t, and multiplied by probability of 0 particle emitted in time delta t. It may be possible. If all the n particles are detected in time t, then there will be a 0 particle detected in delta t time. Or n minus 1 particle is detected in time t, and the extra time interval delta t, there will be a 1 particle. In this process you can add, and you can add p n minus 2 t and p2 delta t, and in this way you can add many terms, p n minus 3 delta t p3. But from the very assumption p1 t is equals to lambda delta t, but in the time interval delta t, that is our assumption, delta is small enough to consider 2 particles are emitted in this interval. So that's why all these terms, all these higher order terms is 0, because our interval is chosen in that way. In that way, there will be only 1 particle will be emitted in that interval. That is our main master equation, and approximately we can say this is an approximation of course this is an approximation under this, or you can say exact under this assumption. And this is the master equation, and what will be that basically, and p0 delta t means the probability of actually happening detecting the 0 particle. That means 1 minus lambda delta t is the probability of actually complementary. It is basically p1 delta t. The 1 minus lambda delta t is the probability of happening or detecting the 0 events. And in this way, and p1 delta t is already lambda delta t. That means p t plus delta t, that is equals to pnt, and you just distribute it, lambda delta t pnt, pn minus 1 t lambda delta t. This is a very simple algebra. And after that, if we write in this way, pn t plus delta t minus of this thing pn t divided by delta t, and we can write lambda pn minus 1 t minus lambda pn t. Letting delta t tends to 0 in the limiting situation, we can write it as a differential dpn dt, dpn function of t dt, that is equals to lambda pn minus 1 t minus lambda pn t. Now I am considering the different situations. Suppose n equals to 0. N equals to 0, that means dp0 dt, that is equals to lambda p0, and from here if we integrate this, p0 equals to some constant a e to the power minus lambda t. And you know, in time interval 0 time interval, the 0 particle will be detected. That means that is a certain event. That means the probability is 1. That means a equals to 1, and p0 equals to e to the power exponential distribution. Now I am putting n equals to 1 in this equation, and what will be that? Basically lambda p0, and here lambda p0, because this term there is no such term, pn minus 1, because negative number cannot be possible. Negative number of events cannot be possible. And dp1 dt, that is equals to lambda p0 t and minus lambda p1 t. And if you just integrate this, that is and if you integrate this equation, that is a serious home task for you, and p1 t, that is equals to, that will be lambda t e to the power minus lambda t. That can be easily solved. It is a standard way. I am not digressing to prove this. I am just elucidate the process how to get that. And if you successively you do this, you will get for nth process, it will be a lambda t to the power n by n factorial times e to the power minus lambda t, where n equals to 0, 1, 2, infinity, up to infinity. It can be shown for n equals to 2, 3, 4, 5, and by inductive logic I can arrive at this equation. And for t equals to 1, it becomes lambda to the power n times e to the power minus lambda by n factorial. As we already know, px, suppose x is some random variable, some constant, some parameter, lambda to the power x e to the power minus lambda divided by lambda x factorial. That is basically the Poisson distribution. This is basically the for unit time, this is basically the Poisson distribution. This is a factorial, And if you take x average, you know lambda, and lambda sigma square is lambda. And here n average is average number of particles that is emitted, which is basically the lambda, average number of particles per unit time. That is very important. And exactly n counts per unit time. That is our main equation, and we have derived the Poisson distribution from the point of view of queuing process or waiting time process. And this is a very vital and very important way of looking at the Poisson distribution.